Hi everybody. So in this video we continue with chapter 6, modeling real-life phenomena. Specifically we're going to go into section 6.4, exponential models. So exponential models arise in situations where the rate of change is a constant factor. That is, when the next value is found by multiplying by a constant factor. This sort of change can produce surprising results. We're going to see this in a video based on an ancient story.
This is an old story, but it reminds us of the surprises we can get when even a small number like 2 is multiplied by itself many times. King Shahram of India was so pleased when his Grand Vizier Sisabendar presented him with the game of chess that he asked Bendar to name his own reward. The request was so modest that the happy king immediately complied. What the Grand Vizier had asked was this: that 1 grain of wheat be placed on the first square of the chessboard, 2 grains on the second square, 4 on the third, 8 on the fourth, 16 on the fifth square, and so on, doubling the amount of wheat on each succeeding square until all 64 squares were accounted for. When the king's steward had gotten to the 17th square, the table was well filled. By the 26th square, the chamber held considerable wheat, and a nervous king ordered the steward to speed up the count. When 42 squares were accounted for, the palace itself was swamped. Now fit to be tied, King Shahram learns from the court mathematician that had the process continued, the wheat required would have covered all India to a depth of over 50 feet. Incidentally, laying this many grains of wheat end to end also does something rather spectacular. They would stretch from the Earth, beyond the Sun, past the orbits of the planets, far out across the galaxy to the star Alpha Centauri, 4 light years away. They would then stretch back to Earth, back to Alpha Centauri, and back to the Earth again.
So let's begin with example 6.10. And it says, suppose that a population of wombats is increasing at 7% per annum. So in case you're wondering what wombats are, it's these cute little animals that are native to Australia. The population at the beginning of 2018 is recorded to be 240 individuals. Assume that this rate of growth remains constant. Part A, develop a model for the population of wombats over time. So before we do this, we have to take into account the general form of an exponential model. A quantity that is changing at a fixed fractional rate p per fixed period can be modeled by the exponential function f of x equals k times parenthesis 1 plus p to the power of x, where k is the initial value of the quantity. Now here they don't mention that p is going to be the rate of change, and that x is time. In most instances, you're going to find t instead of x. Now notice that this is very similar to compound interest. Basically, compound interest is also an exponential model. So in this particular case, we would have that the rate is 7% and that the initial amount is 240 individuals, as we can see here. So we could model this as f of x is equal to 240 times 1 plus 7%. Now write the rate as 0.07 and this to the power of x. So notice that we can rewrite this as f of x is equal to 240 times 1.07 to the power of x. For part B, it says Use your model to predict the number of wombats at the beginning of 2025. So notice that the population is recorded at the beginning of 2018. So we need to know how many years have gone by. So all we have to do is subtract 2025 minus 2018, and this equals 7. So we need to know what f of 7 is. And this is simply going to be 240 times 1.07 to the power of 7. And if you plug this into the calculator, you're going to get 385 wombats. For part C, they want us to find out how long will it take the population of wombats to double. So that means when is the model that we found. Remember that it's f of x is equal to 240 times 1.07 to the x. So when is this going to equal double the population? So that would be 480. For this, we're going to use the GDC. Okay, so in the GDC, under apps, there is a function that says solver. That's one way to do it. You can use the solver. In my case, I don't have the solver in this emulator, so I'm going to do it graphically. So to do it graphically, we go to y equals, and first we plug the function 240 times 1.07 to the power of x. And below that, we plug in y equals 480. So the solution to this problem is finding where these two lines intersect, where the exponential function and the linear function are going to intersect. Before we graph it, let's be sure that we have the appropriate window. So for the years from 0 to 50 should be enough. And for the amount of wombats, notice that we want to get to 480. So from 0 to 500 would be fine. So now we hit graph. And notice that we have both lines there. I'm going to change the window a little bit because I want it to be higher. So instead of 500, let's make it 700. That'll give us a better picture. So once we have both lines displayed, we need to find their intersection. For that, we go to second, calculate, and option 5, intersect. So it's going to say first curve. So move the cursor until you see it to see what they mean by the first curve. And there it is. So the first curve is the exponential function. Hit enter, and it's going to say second curve. And you can see that the cursor is on the second line. Hit enter again. It says guess. Click on enter, and there it is. Notice that it would take 10.2 years to reach the value of 480. So the answer here is 10.2 years. Now notice that I'm always rounding to 3 significant figures. For part D, it says an ecologist estimates that this region can sustain at most 1,000 wombats. In what year will the population reach 1,000 wombats? So this is exactly the same, but we would equal it to 1,000. So you go 240 times 1.07 to the x is equal to 1,000. And to solve it, we'll use the GDC as well. So instead of 480, we want to put in 1,000. And we want to make sure we have a window that is big enough. So instead of 700, we want 1,200. And let's hit graph. And there we have both lines. So now we're going to do the same thing we did before. We find the intersect. Option 5, again, first curve, hit enter. Second curve, guess, and there it is. It would take approximately 21.1 years. Again, rounded to 3 significant figures. But the question is, in what year will the population reach 1,000 wombats? So it has to be 2018, which is the beginning, plus 21.1, and this is going to equal 2039.1. So the answer should be during the year 2039. So let's continue with example 6.11. And it says, the value of a certain new car decreases according to the model V of t equals 39,000 times 0.72 to the power of t plus 1,000, where V of t represents the value in euros of the car t years after it is purchased. Part A, find the original purchase price of the car. So for that, we have to see what V of 0 is. So V of 0 is equal to 39,000 times 0.72 to the power of 0 plus 1,000. Now remember that any number to the power of 0 is equal to 1. So this is just 39,000 plus 1,000, and this is 40,000 euros. Part B, interpret the meaning of the value 1,000 in the model. So what does this mean? What does it represent? This is what is called a residual value. It would be the value of the car as scrap. So we can just write here, scrap. For C, calculate when the value of the car will be half its original price. So in other words, when is 39,000 times 0.72 to the power of t plus 1,000 equal to 20,000. Now you guys already know how to do this in the graphing calculator, and you're going to get that t is equal to approximately 2.19 years. It's common in science applications to use a different form of the exponential model. Instead of changing the base of the exponent by adding the fractional rate p to 1, we add a parameter r as a factor in the exponent and use the special base e. So e is Euler's number. F of x is equal to k times e to the power of r times x. The value of r is often determined through experimental evidence. It turns out that the two models are equivalent, as example 6.12 will show. So next we have example 6.12, and it says, a student measures the temperature of a cup of coffee at regular intervals in a room where the temperature is 20 degrees Celsius. Table 6.8 shows her data. So we have it right here. Part A, develop an exponential model of the form f of x is equal to k times e to the power of r times x plus c, where k, r, and c are constants to be determined. So for part A, we need to find or develop the exponential model based on the information that we have. Now notice that we have a residual value, which is a room temperature. So C is 20. Now, in order to find K, let's use the fact that at time 0, the temperature is 95 degrees Celsius. So in other words, F of 0 is equal to 95. So we would say that 95 is equal to K times Euler's number to the power of R times 0 plus 20. Now notice that this is just going to equal 1. So we have that K is going to be 95 minus 20, which is 75. So now we have K. All we're missing is R, which is the rate of change. But we have that F of 1 right here from the table. We have that F of 1 is equal to 79. So we can use this fact to find the rate. So I can write this as 79 is equal to K, which we know now is 75. So 75 times Euler's number to the power of the rate times 1, which is the value for x, plus 20. So we can subtract 20 from both sides, and we're going to get that 59 is equal to 75 times e to the r. Send the 75 to divide, and we're going to get 0.787 is equal to e to the r. Now, Euler's number is the inverse of something called natural logarithm. So if we apply the natural logarithm to both sides of this equation, we can rewrite it as r is equal to the natural logarithm of 0.787. And from here, we will get that r is equal to negative 0.240. So we have all the data we needed for the model. In other words, the model is going to be f of x is equal to 75 times Euler's number to the power of minus 0.240 times x plus 20. So now that we have the model, we're ready for part B. So in part B, they ask us to use the model to find the temperature of the coffee after 8 minutes. So we said the model is f of x is equal to 75 times Euler's number to the power of minus 0.240 times x plus 20. So we need to find f of 8. And that's going to be the same expression, but instead of x, we will plug in 8, right? So 75, Euler's number to the power of minus 0.240 times 8 plus 20. Plug that into the calculator, and it's going to give you 31.0 degrees Celsius. For part C, it says, use your model to predict when the temperature of the coffee will reach room temperature to 3 significant figures. So room temperature is 20 degrees Celsius. So notice that we can say 75 times Euler's number to the power of minus 0.240x plus 20. When is this going to equal 20? Or, notice that I can subtract 20 from both sides, or 75 Euler's number to the power of minus 0.240x is equal to 0. Now, there is an impossibility here, and it's the fact that these functions with base e are never equal to 0. So what we can do is play a trick. Let's write a number here that is very close to 0, and that should help us solve the problem. So let's say 0.05. So let's solve this. Now notice that I can divide both sides by 75. And if I do that, I'm going to get Euler's number to the power of minus 0.240x is equal to a very small number, 6.67 times 10 to the power of negative 4. So again, here we use natural logarithm on both sides. Now the natural logarithm will get rid of Euler's number. So we're going to end up with minus 0.240x is equal to the natural logarithm of 6.67 times 10 to the negative 4. Now divide both sides by negative 0.240, and we're going to get that x is equal to 30.5 approximately. So 30.5 minutes. Now for part D, they want us to find the rate of decrease in the difference between the coffee temperature and room temperature as a percentage per minute. So for this, we're going to need a table. So from the previous table, 6.8, we have this information here, the time in minutes and the temperature. Now the room temperature is 20 degrees Celsius. Notice that the difference in the first case is going to be 75. In the second case, 79 minus 20, it's going to be 59, then 46.41, 36.51, 28.72. So if we want to find what the difference in the change is, or the percentage of change, we do 59 minus 75 divided by 75 times 100. And this is going to give us this number here, negative 21.3%. For the next case, we go 46.41 minus 59 divided by 59 times 100, and we're also going to get negative 21.3%, and so forth. So that means that the rate of decrease in the difference between the coffee temperature and the room temperature is negative 21.3%. Okay, so now let's talk about a graphical interpretation. It's worth looking at the graphs of the last few models. Notice that in each case, the location of the horizontal asymptotes is given by the value of c in the model f of x equals k times 1 plus p to the x plus c. In the wombats example, 6.10, c equals 0, so the asymptote is at y equals 0. That's this case over here. In that context, the horizontal asymptote is not meaningful because it occurs in negative years since 2018. So 2018 is represented by 0 here on the years, and the horizontal asymptote occurs in the negative, as they're saying. So there doesn't seem to be a useful interpretation of it. In the car example, 6.11, not shown, c equals 1,000, so the asymptote is at y equals 1,000. In that context, it represents the eventual residual value of the car. For the coffee example in 6.12, figure 6.26, which is right here, c equals 20. We can see that in the graph, c equals 20. So the asymptote is y equals 20. In that context, it represents the room temperature, which is the eventual temperature of the coffee. Although, because it's an asymptote, it actually never reaches 20, as we explained during the example. A common use of exponential functions is half-life calculations. So what is half-life? Half-life refers to a process of radioactive decay. A substance's half-life is the average amount of time it takes for the activity of a substance to decrease to half its previous value. Activity refers to the number of nuclei decaying at any time, measured in decays per second, or becquerel. For example, the half-life of fermium-253 is 3 days. If the activity of a sample of fermium-253 is 100 becquerel, then after 3 days, the activity will have decreased to 50 becquerel. After another 3 days, the activity will be 25 becquerel. So we finish this video with example 6.13. And it says, all living things on Earth continuously take in carbon. Since a tiny fraction of the carbon on Earth is a naturally occurring radioactive isotope, carbon-14, the fraction of carbon-14 in all living things is constant. However, once an organism dies, it stops taking in carbon, and the carbon-14 in its body begins to decay. Because of this, scientists can use carbon-14 dating to determine how many years have passed since an organism died. A model for carbon-14 dating is A of t equals k times e to the power of minus 0.000121 times t, where A of t is the activity of carbon-14 remaining from an initial activity k after t years. Part A, show that the half-life of carbon-14 is 5,730 years to three significant figures. So they give us the model, and they say A of t is equal to k times Euler's number to the power of minus 0.000121t. And this is all we have. Now, you might think, I don't have k. How can I solve this? How can I find k? Well, we don't need it because basically they're saying that we have to show that the half-life of carbon-14 is 5,730 years. Now, the half-life, remember, by definition is when half of the activity remains. So let's suppose we have that k equals 2. Then we could write this as A of t is equal to 2 times Euler's number to the minus 0.000121t. Okay, so what would be the half of 2? Well, it's going to be 1, right? So just 1 is equal to 2 times Euler's number to the minus 0.000121t. Now, notice that if I send the 2 to divide, I'm just going to have 1/2 or 0.5 is equal to e to the minus 0.000121t. So it doesn't matter what we use here, right? If we had 6, this would be 3. So if this was 6, then we would have 3 here. We end up with 0.5. So half of the activity left. Okay, so we can solve this again using natural logarithms, remember? So this means that, continuing over here, it means that natural logarithm of 0.5 is equal to minus 0.000121 times t. And then we divide this by this, right? So we would end up getting that t is equal to 5,728.5. But this rounded to three significant figures is 5,730 years. For part B, it says, a tissue sample from a body discovered on the border between Austria and Italy has an average activity of 6.92 becquerel. A sample of live tissue of the same size has an average activity of 12 becquerel. Determine the age of the sample. So this is very similar to the previous example, or to the previous part of this example, because we could just write this as 6.92, right? That's the average activity of the tissue that was discovered, is equal to 12, which is the initial activity it would have had, comparable to live tissue, right? So 12 e to the power of, again, minus 0.000121t. Now, you guys already know how to solve this with logarithms, but you should get that t is approximately 4,550 years, rounded to three significant figures.